Hi everyone, my name is Grigory Fursin, I'm CTO of Dividity, and I'm glad to see many of you here after lunch. After lunch is usually not a good time, so hopefully my talk will not be so complex and will help you digest your food. And I will not focus so much maybe on research, but actually on our open source framework, which helps you automate research. This is usually a topic which is not often covered, surprisingly, and I think it's now becoming very important, and I hope I will persuade you using it. We have a growing number of users, so this work is done in collaboration with ARM, with General Motors, and with Raspberry Pi Foundation, and so on. So it's real work. So far, at this summit, you saw many interesting discussions about how to make our software and hardware efficient for emerging workloads like deep learning and so on. And of course, the main challenge is that we need to run those workloads across really many form factors, and starting from tiny sensors to supercomputers. And at the same time, there are really many constraints nowadays which you need to fit in. And it's not only speed, now you look at energy, accuracy, and all the other costs. And of course, ARM is not the only company which is working on this. There are many companies and universities which are trying to build their own solutions. And there is kind of a hot race to develop all the cool AI applications at the moment. The problem now is that all this kind of fun race led to what Masayoshi Son mentioned as a Cambrian AI explosion. And in fact, I would say that it's kind of technological software and hardware mess. Because everything is changing all the time. So if you're a researcher or if you're an end user, navigating through all this mess nowadays is extremely complex. And finding a good solution for your own application is really tough. So just to mention that in our startup, we got some interesting people with different backgrounds, and it's spawning from quantum mechanics and physics and machine learning to systems design. So what we started doing, we started helping end users, companies like General Motors, making competitive analysis of the whole stack, machine learning stack, ranging from models to software and hardware. And from the public information, which I can mention, is basically it's understandable. They are looking for a solution for, say, self-driving cars. And the need out there are many solutions, and they need to find the best solution, which is, for example, following your frames per second. It has an energy budget, and so on. At the same time, we work with companies like ARM, who design their chips, and they benchmark them, and they also want to know how their chips, future chips, will work across real workloads, not just benchmarks. As you know, that when you benchmark your hardware, then you move it on the market, and then you show General Motors that the results are fantastic, then they run their real applications, and then results are not fantastic anymore. And then there is a problem. And the same we also work with, now increasingly with universities, our educational programs, where we actually help them design software and hardware, but comparing it with solutions which are already available on the market, or maybe even not available on the market, but will be there in a year or so. Just to give you an idea about why competitive analysis is important nowadays, and not to make things, not to overcomplicate things, sorry. Let's look at just a simple scenario like image classification. Everyone looks at image classification, standard application, very important, and so on. I will also not cover all the possible hardware which we look at, but I'll look at mostly embedded systems with a power range from 1 to 10 watts. And if you start looking just at again, for end users, what is important as the first step is, say, execution time versus cost of the device when they select the device. And then we start looking at different solutions available out there. So for example, if you look at different frameworks, there are Caffe, TensorFlow available, there are other frameworks available. Underneath technology, you look at the mathematical libraries, and there are also about 4, 5, 6 different libraries available. There are many different data sets, standard data sets available, and of course, not standard, but kind of community-based or internal proprietary ones. And if you start just running those classification problems and plotting them on this two-dimensional graph, you will see that from, say, 700 devices, which you can look at, which are actually available out there now, that you will have only like just a couple of good solutions out here, which fits your, which fits end user. So in terms of execution time, so it's, they can make like real life processing, and in terms of cost. And all the rest is basically, it may extinct, and it's wasted effort. And if you're a researcher, you want to know that you are far from winning solutions pretty fast. So if you're somewhere here, it doesn't mean that the solution is bad. It's also maybe unoptimized and so on. So then you need to start looking at the whole software hardware stack, start optimizing it. And of course, it's very tedious and time consuming, because at each step, at each level of the software hardware design, you start having explosion in all your choices, possibilities. And if you go further inside compilers, or if you look at models, topology, and so on, you have really an infinite design optimization space. So it's really complex. And when I look at the different research that usually you take like one or two possible paths, you explore it for 2-3 years, and when you are done, you either publish paper or you realize that your solution was not good. So we want to avoid this. And what we decided to do is, okay, the buzzword everyone now speaks about that, oh, we need to reinvent computer engineering. Of course we need. How? And what we want to do is that we wanted to provide a framework and a repository where everyone could contribute their benchmarking and optimization and start sharing results, understanding the results, how far they are from optimal, and collaboratively improve their solution. So the idea is good and sounds kind of simple. Implementation is always difficult. So we have been working on this topic for about 7 years, 6 years. And each time we're building next generation of framework. And I think the last framework, what we came up with, Collective Knowledge, is basically a simple plugin-based workflow framework. So with our background in other domains, we realized that, in computer engineering, we don't have common experimental framework. And there are reasons for that, because again, the software is changing and so on, hardware is changing. So what we do is that we provide, for each of this component within the system, we just basically provide their own wrappers, very lightweight Python wrappers. But they have common API, so we unify API for each of this component. And we'll go through the whole stack, from algorithms to your frameworks, which you can have, your compilers, and down to hardware. And this framework, again, I just want to thank our first sponsors 2 years ago. So it was European Framework, FP7 Framework, and Tetracom Project and ARM, who initially funded this project 3 years ago. So what happened with this framework? Sorry for this small outline. Afterwards, we start sharing different plugins for this framework with the community. And basically, all available models, such as AlexNet, GoogleNet, there are mobile nets and so on. We start sharing those plugins for them with the community, and we also unify the meta information, how you can plug it in to this framework. At the same time, we start sharing wrappers around all available AI frameworks out there, so Caffe, Caffe2, CNTK, MXNet. Then we take those workflows, and it becomes really a tiny Python code, which we start sharing as well in the repository, so everyone can take some kind of scenario workflow which does image classification, for example, or object detection, run it on their system. And the fun part now is that usually when you do research, you are very limited with 1 or 2 platforms where you can run your experiments. And now, since you have a common framework, you can actually crowdsource your experiments across hundreds of different machines and so on. And then you can start collecting results, because you have those common APIs and so on, within some public or private repository. Repository doesn't have to be public, so with companies, some parts of the repository are private. But with the community, of course, we work a lot, and everything is becoming open source, open at the Synology.org repo. So you can go there and you can see some of the graphs which I will show you today. Now, I wanted to mention a few concepts behind CK, because as I said, it's now taking off. We have more and more users, so I hope it may be useful for you. And the starting time may be complex if you don't know anything about it, so I want to give you some ideas behind it. What we notice is, doing collaborative research for many years with different groups, you know that everyone has their own scripts to do some specific common tasks, like downloading, I don't know, TensorFlow, installing it, preparing your ImageNet for training, and so on. Compiling and running some front end for image classification, or if you do tuning of your BLAS libraries and so on. And everyone has their own kind of scripts with actions. So what we did is that for each of this script, basically, we provide our own what we call CK Python module. And for each of the common action, we provide kind of an API within this Python module, so kind of simple thing. And if you start looking at many repositories which our users are sharing at GitHub and so on, you will have always the same structure now. So the structure, the first level directory, which you will see, basically the name of your module. And then what we do is that we provide a holder for all your artifacts which are there. So ImageNet, we are not converting it, we're just preparing a second level directory with a name, and we provide some JSON file, specific meta information about it, and then we just copy original artifact, or we provide a way to download it from the system. But now the whole thing is kind of what is important here is one person wrote, for example, their own program module and found out a way how to compile and run the program, but then everyone else within the group can start reusing this module instead of writing your own scripts and so on. So this puts us on the same page. And then basically collective knowledge framework, it's really tiny framework, Python framework, which you install on Windows, Linux, macOS, and so on with pip. And then you basically have those functions which you pull your repository and then you start calling with the CK front end all those functions and modules. And that's all. I'm skipping some other things about how we unify input and output, but it's basically we serialize everything into JSON. But sounds like a simple concept, why do we need it? It allows us very actually complex things. For example, all our workflows when we train a model, when we run a model, run inference and so on different platforms, we now provided all those pipelines, and you can see those repositories here if you want. And basically, the front end for end users say CK run image classification. So now all the rest underneath is hidden from a user. But someone else has to still write those wrappers. And of course, we provided within 1 or 2 years with collaboration with all our partners, we provided lots of wrappers. What they do, they basically adapt to the environment. Another problem is we always, when we write our own scripts, we hardwire names of compilers, of tools, and so on. So when compiler or tool is changing, API changes, so you are doomed. We have a real example when obviously we have been using Caffe 1 for a while with our end users. And when we just prepared and released all the workflows, Caffe 2 was released and no one was expecting it. And for the project, it was a disaster. So it was like you could suicide because you have to change the whole project. With our wrappers, because it was abstracted, we just provided a package for Caffe 2 and we just provided detection of Caffe 2 and transferred all your converted underneath all the image, all the data sets and so on to Caffe 2. So you abstracted from this, you didn't even see it. So researcher was really continued doing research as if there was no change. And this is a really powerful thing. Now, even though I mentioned that I'm not speaking much about research, of course there is some research going on. And of course, for 20 years, everyone was doing auto-tuning. And with all, when you have all the topology of your models, you have many compiler transformations, you have at all levels, you have different parameters. So what we do here is that auto-tuning and modeling of a behavior comes kind of as a side effect, because all those wrappers, again, we can start exposing in this information flow just several keys which are really related kind of to physics. So you model your behavior, which is your keys. These are your keys for execution time, code size, compilation time, energy, and so on. These are they depend on your choices underneath, and you also expose gradually different choices within the system, your model topology, your parameters, your compiler flags, possibly transformations within your math libraries, you gradually expose them. Some features, and the system state, like GPU frequency, CPU frequency, and so on. And then we basically start modeling the coarse-grained behavior of your system and trying to optimize it. So when we have it, basically, since we can crowdsource those workflows across many users, we can start running experiments at different people, and we can slightly tweak our choices, and then we can continuously monitor the behavior. And then this means that we kind of crowdsource auto-tuning as well, and we'll continuously search for better solutions. And then since we also share them, we can always find just keep the best solutions on this Pareto or whatever your frontier. And then basically collaboratively people start optimizing their solutions at the same time. And then of course all the other things like modeling behavior, which is very important when you design next generation of hardware, it's all come to place as well. And it's kind of as a side effect of this unification. Now, some real experiments which we're doing, they're public experiments. What we have so far, and this everyone can use it actually now, is we converted, we started from object classification, object detection. Actually, there is much more coming up in a few months. We use Caffe, Caffe2, and TensorFlow. We have multiple libraries. And we provided much more data sets. We converted everything to CK. What we started analyzing is we still look at the execution time, but we also start looking at model accuracy, model size, device cost, and also power consumption. These are all the things which actually, if you look at all the research papers here, I think it covers most of the research which is needed, or experiments which you need to run. And then what is happening is we also provided a fun application, Android application, where you can actually download it if you look at this QR code. And this application actually connects to CK repository, downloads you slightly differently optimized versions of your Caffe, TensorFlow, different models, and so on. It runs it on your device. It measures different characteristics and sends it back to us. And then again, we're in a live repository. We see all the updates so from different users. So each day it's kind of updating. It's really fun to see. So up to now, we released this Android application about 5 months ago. And up to now, there was about 1,000 downloads. We got about 700 distinct platforms participating. So when you do your own research, you usually compare your results against 1 or 2 platforms. And it's already hard. So here for free, we get really numerous platforms. We have 200 distinct CPUs, 100 distinct GPUs, and so on. So power range for these experiments is still quite small, but also, of course, you can add all the other dimensions there, which we are doing actually with other companies when you look at more powerful GPUs for supercomputers or oppositely tiny IoT devices. And what is important now that we continue showing those frontiers, but then the frontiers obviously depend on your scenario. So for one customer, we still need, for example, to find the best execution time versus cost. Again, when you have a mass production, you care about this. But then if you want a better accuracy, what is interesting is that suddenly your frontiers changes, and it's kind of normal that if you want a better accuracy, of course, it's more expensive and a bit slower because you need a big model usually and so on. But this allows you to kind of convert all your research into kind of data science. And it's really enabled collaborative research now. Just 2 more slides, and I think I have 3 minutes. What I'm telling you here, it's still not really proper optimization. We're just playing with coarse-grained choices. But then we had a task, and we started looking at one of those platforms, Firefly, which is an interesting platform. It's some kind of not too cheap, not too expensive. It's working not too bad. And we thought about how can we optimize it further. And then we started looking at different auto-tuners. And as I mentioned, we can easily plug in all the different auto-tuners which are out there, or even do our own auto-tuning. So here, an interesting example, we have been collaborating with Cedric Nugerten from TomTom, who created this nice OpenCL-based BLAS library. And it has many optimizations which you can play with, and with many ranges. And basically, we plugged it into our framework. We plugged it into Caffe, so it wasn't optimized outside with some random data sets. It was really inside the real application. But then whenever you run your image classification, each time we're tuning this library. And what we'll show you, just the last slide, just to give you a hint of what you can do with this kind of approach, is the following. So here, what I show on the graph, so for 3 different models, we show frames per second, basically. And we ran Caffe, and we compare five different libraries. So underneath math libraries was libDNN, CLBLAST, VNCL, CLBLAST. When we say CLBLAST, it was auto-tuned. So DVDT actually comes from acceleration, if someone didn't notice that. And OpenBLAST. And then we ran it on GPU and CPU. And this is ARM-based architecture, both CPU and GPU. So and what is happening is OpenBLAST, if you also tune batch sizes and so on, CPU is working really well. And there is a famous thing that if nowadays you try to run models on your GPU, the performance is really bad. And if you have been at the BOF by Pete, so he was also mentioning this. So here with auto-tuning, we actually got really nearly to CPU performance on this platform. And it's 4, 6, 7x speedups. So in such case, we can actually start really using heterogeneous kind of processing. So we can start running at the same time parts of your models on CPU and on GPU, but you really need auto-tuning. And this auto-tuning, as I mentioned, again, it came as a side effect of our unification. So we're not really doing special yet another auto-tuning framework for that. And finally, we share results, everyone can reproduce them and build upon them, because again, you have the common framework. So that's how we work with the community. The last slide, just as a conclusion. We now have a growing community around this approach. I'm very glad and I'm very thankful to all these partners who are using collective knowledge framework. But it's only very, very beginning, and there is really a lot to be done. And we're building a new consortium. Hello? Yeah. We're building a new academic industrial consortium, so who would participate in those kind of open competitions and so on. There is lots of interest, and if any of you are interested to participate, just get in touch, because it's ongoing work. We will collaborate with several conferences, and I think it's a really interesting approach. The same, we continue with the community. We continue sharing all those artifacts which you use for your research. We unify them. We provide JSON API, so you can basically start plugging in all those artifacts to your research workflows. And instead of spending months and months on preparing experimentation, you can really spend one minute to start your experiments and then do innovation. Finally, a couple of more things. We improve models, and we also find missing features because we crowdsource all this approach. We crowdsource modeling. And our last hope, where we're moving towards, is online learning. So we want to actually distribute learning across many different devices. We have all the technology for this. So partners are welcome for this. OK, thank you very much.